Hi everyone. Today we are going to talk about decision trees. We will see what they are, how they work, and understand them with a simple example. So let's get started. Have you ever wondered how a computer makes a decision? Whether it's deciding if an email is spam, predicting what a customer will buy something, or even classifying the data. In this video, we are going to understand how a decision tree makes these decisions step by step in a really simple way. Okay, so first thing is decision tree is a type of supervised learning algorithm. Now, what do you mean by supervised learning? Supervised learning means we give input as well as output to the model. Okay, that is, we say that it in presence of a supervisor, but there is no supervisor as such. Our output acts like a supervisor. To take an analogy of teaching to a small kid, so let's say we are teaching the child the difference between an apple and an orange. Okay, so what we may do, we may take the actual objects, that is an apple and an orange, and we may show it to the child. We may say, look at this is an apple. Okay, this is red in color. It has got some white stripes on it. Okay, so this is description of an apple. Okay, so we give description of an apple and we also label it. Also label it means we say that this is an apple. This is how we teach a child. Similarly, in machine learning also, we teach the model or the model learns from the features that we provide and the labels that we provide. So this is a type of supervised learning. In unsupervised, we do not provide output data. Okay. Now, classification is a type of supervised learning. Classification predicts categorical class labels. And the typical applications are credit loan approval, medical diagnosis, if a tumor is cancerous or benign. So these are the two classes, cancerous or benign. Fraud detection, that is if a transaction is fraudulent or no, yes or no. So these are the classes. Web page categorization, which category of web page it is. So this could be a multi-class classification. Today we are going to see ID3 algorithm. ID3 stands for Iterative Dichotomizer Tree. It is a classification algorithm that follows a greedy approach of building a decision tree. Greedy approach means it selects the best attribute. Currently, greedy approach is that which says choose the current winner. Okay, so it selects the best attribute that yields maximum information gain, or we can say minimum entropy. Okay, now these are the steps of ID3 algorithm. You calculate entropy of the entire data set first. Then for every attribute, calculate entropy for all its categorical values. Then you calculate information gain of that attribute. You find the feature with maximum information gain. That becomes, for the very first time, it becomes the root of your decision tree. And repeat it until we get the desired tree. Now, our aim is to get a decision tree which is shorter so that we can come to a conclusion as early as possible. Okay. Now, let us understand these terms. What is entropy? Entropy is a measure of randomness or uncertainty in the data. Now, let us understand with a coin toss problem. So, consider a coin toss problem. The probability of getting a head or a tail is the same, that is 0.5. So, the formula of entropy becomes minus p log of p to the base 2 minus q log of q to the base 2. So, here p and q, both the values are 0.5 because our coin is an unbiased coin. That means the probability of getting either a head or a tail is the same. Okay. Therefore, entropy is minus 0.5 log of 0.5 to the base 2 minus 0.5 log of 0.5 to the base 2. If you'll calculate this, you will get this as 1. Meaning, entropy is highest and chances of happening of both the outcomes are equal. Okay. And therefore, in this example, we got highest entropy. Now, let's say our coin is a biased coin. Biased coin means, let's say the coin will always give a tail. Okay, so here the entropy becomes 0 as there is no uncertainty because a coin has to give a tail every time. Okay, so this is this is entropy. Now look here at 0.5. Okay, for binary classification at 0.5, both the outcomes have got equal chance. Okay, here the entropy is max. Okay, and if for 0 or for 1, the entropy is 0. Now what is information gain? Information gain is calculated for a split by subtracting the weighted entropies of each branch from the original information gain, from the original entropy. Okay, now see what we are doing here. We are summing up the entropies of all its categorical values. So for example, if you take this, this classic example of play tennis, let us look at the attribute outlook. As we can see, there are three distinct values: sunny, overcast, rain. Okay, so the three values are sunny, overcast, and rain. So what we'll do, we'll calculate entropy of sunny. Okay, we'll calculate entropy of overcast, we'll calculate entropy of rain. Okay, and then we are going to sum it up. We are not simply going to sum it up. We are going to take weighted entropies and we are going to sum it up. Okay, and that we will subtract from the entropy of the whole data set. And this is how we will get information gain of outlook. Okay, now let us start with the problem. Okay, so this is a classic problem of play tennis. So the inputs are outlook, temperature, humidity, wind. Okay, and play tennis is the output column. Okay, this large column is our output column. It has got two values, no and yes. Okay, outlook, as we can see, there are three distinct values: sunny, overcast, and rain. Okay, so we will start with the problem. The first step is we will calculate entropy of the data set. Okay, now how do we calculate entropy of the data set? Now here we have count the number of yeses that we have and count the number of no's that we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 yeses and count the number of no's. 1, 2, 3, 4, 5. And we have 5 no's. Okay, so entropy of the data set becomes, okay, see there are 9 yeses and 5 no's. So 9 positive and 5 negative we can say. Therefore, entropy of the data set is minus 9 by 14 log of 9 by 14 to the base 2 minus 5 by 14 log of 5 by 14 to the base 2. So if we calculate this, this will come out to 0.94. Okay, so we have done the first step, that is we have calculated entropy of the data set. Now we'll move on to the second step, that is for each attribute calculate entropy for all its categorical values. So let us start with that. Okay, let's take the first one. Let's consider outlook. Okay, so what are the distinct values that we have in outlook? Sunny, overcast, and rain. Okay, now let us start with sunny. Count how many sunny and yeses are there and how many sunny and no's are there. Okay, so this is the data set. Okay, sunny and no, sunny and no, sunny and no, 3, sunny and yes, sunny and yes. So there are 2 yeses and 3 no's. Therefore, entropy of S sunny is minus 2 by 5 log of 2 by 5 to the base 2 minus 3 by 5 log of 3 by 5 to the base 2. Why 5? Because there are 5 instances of sunny. Out of that, 2 will give you yes and 3 will give you no. Okay, so calculate this. It comes out to 0.971. Okay, now let us move on to the next one, that is overcast. Okay, count how many, let's see, overcast and yes, overcast and yes, overcast and yes, overcast and yes. So there are all yeses. Okay, all yeses means 4 positive, 0 negative. Therefore, entropy of S overcast is 0 because there is no uncertainty. Okay, whenever it is overcast, you'll be going out and playing tennis, as we got all 4 yeses. Okay, so entropy is 0 for S overcast. Let's proceed further with rain. So there, let's see, rain, rain and yes, rain and yes. So 2 yeses so far, rain and no, rain and yes, 3 yeses, rain and no. Okay, so 3 yeses and 2 no's. Therefore, entropy of rain becomes minus 3 by 5 log of 3 by 5 to the base 2 minus 2 by 5 log of 2 by 5 to the base 2, which again, more this and this, they're same only. Only thing is this term is over here and this term is over here. So it is 0.971. Okay, now let us calculate gain of outlook. Okay, what is the formula of gain? Entropy of the whole data set minus summation of, okay, summation of weighted entropies of all its categorical values. Now for outlook, there are three values: sunny, overcast and rain. So, and we have already calculated entropies of all the three values. Okay, only thing left will be calculation of this weights. Okay, so let us put the values. So gain of S with respect to outlook is 0.94 entropy of S minus weights of, see, let us take V as sunny first. Okay, so mod of S sunny upon mod of S. Now, as we said, or as we saw earlier, there are 5 instances of sunny. Therefore, mod of SV is 5. And total, how many records we have in the data set? 14. So, 5 by 14 into 0.971. Okay, similarly for overcast, mod of SV, how many instances of overcast are there? 4 out of 14 into entropy of overcast is 0 plus how many instances of rain are there? 5. 5 upon 14 into entropy of rain, which is 0.971. So if we calculate this, it will come out to 0.2464. Okay, so what we have done is we have calculated weighted entropies for all its categorical values. We have summed it up and then subtracted that from the entropy of the data set. Similarly, we'll move on to the other feature now. So let's take temperature. Okay, what are the values in temperature? Hot, mild and cool. Okay, now entropy of the data set remains the same, 0.94. Okay, and let's see how many hot and yes and hot and no are there. Okay, so hot and no, hot and no, hot and yes, and hot and yes. So 2 yeses, 2 no's. Okay, you did not write the formula. Even if you'll write, you'll get the same answer. You simply put the value. Entropy of S hot is 1. Okay, as both the outcomes have got equal chance. Okay, let's proceed with mild. Okay, mild and yes, mild and no, mild and yes, mild and yes, mild and no. So in mild, we had 4 yeses and 2 no's. Therefore, entropy of S mild is minus 4 by 6 log of 4 by 6 to the base 2 minus 2 by 6 log of 2 by 6 to the base 2, which comes out to 0.9183. Let us now take cool. Okay, we are done with mild. We will take cool. Okay, cool, cool and yes, cool and no, cool and yes, cool and yes. That's it. Okay, so we had 3 yeses and 1 no. Therefore, entropy of S cool is minus 3 by 4 log of 3 by 4 to the base 2 minus 1 by 4 log of 1 by 4 to the base 2, and the entropy, this will come out to 0.8113. Now let us calculate gain. Okay, gain is equal to entropy of the data set minus, okay, now what we are going to take is mod of SV upon mod of S. Okay, here V belongs to hot, mild and cool. Okay, therefore mod of S hot upon mod of S. Okay, so which comes out to 4 by 14 into entropy of S hot, which is 1. Okay, plus 6 by 14 into 0.9183 plus 4 by 14 into 0.8113. So this will come out to 0.029. Okay, next we are going to do is we are going to consider humidity. Again, we are going to proceed the same way. Then we'll calculate for wind. We will proceed the same way. Next thing that we'll do is we'll compare all the gain values. Okay, gain of the data set with respect to output, or with respect to temperature, humidity, wind. Okay, pick up the one with the highest gain, that is 0.246. Next, what we will do is we will take only sunny data set now instead of the whole data set. So look here, we are going to take only these values. For example, day 1, day 2, day 8, 9 and 11. We are going to only take these records. So we have these records now. Now this is our data set that we are going to consider, and we'll calculate entropy for this data set. Okay, entropy of S sunny. Now we have 2 positives, 3 negatives, and therefore entropy of S sunny is minus 2 by 5 log of 2 by 5 to the base 2 minus 3 by 5 log of 3 by 5 to the base 2, which comes out to 0.97. We have earlier calculated this, so no need of doing the calculation again. We can use the same value. Next, we will calculate for temperature. Okay, now there are 3 values: hot, mild and cool. Okay, for hot, we have hot and no only. Therefore, entropy of S hot is 0. Okay, because we have 0 positives and both are negatives. Consider mild only, we have 1 positive, 1 negative. Therefore, uh, straight away we can write entropy of S mild as 1. Next, consider cool. There's just one record with 1 yes. So 1 positive, 0 negative. Therefore, entropy of S cool is 0. Now, calculate information gain, okay, of S sunny with respect to temperature. So entropy of S sunny minus summation of V belongs to hot, mild, cool, mod of SV upon mod of S into entropy of SV. Okay, now entropy of S sunny, which we calculated as 0.97, we will write it. And now for S hot, okay, S hot, there were 2 records. So mod of 2 upon mod of 5. Mod of S, here S is our sunny data set only. So 2 by 5 into 0 plus 2 by 5 into 1 plus 1 by 5 into 0, and the value comes out to 0.57. Similarly, we'll proceed for humidity. We'll calculate gain for humidity, wind, and we'll compare all the gains. Okay, now the highest is that of humidity. So our next node is humidity. So we will add the next node as humidity to the decision tree. Okay, so for sunny branch, the next node is humidity. Humidity has got 2 values, so we will have 2 branches, high and normal. Now for all highs, it is no, and for all normals, it is yes, as given in our data set. Okay, for all highs, it's no, and for all normal, it was yes. Okay, so we can assign labels to it as no and yes. What is written over here is, in a decision tree, the attribute with the highest information gain is selected as a node because it gives the greatest reduction in uncertainty, that is entropy. Okay. Now, for example, look at this. We are going to select Outlook as our root node. Okay, its values becomes its branches. So we have sunny, overcast and rain. Okay, now for overcast, all were yeses and there were no nos. Therefore, we can easily assign a label yes to it. Okay, but for sunny, we had 3 positives and 2 negatives, and similarly for rain, we had 2 positives and 3 negatives. Okay, so now we cannot assign a label because there were some positives and some negatives. Okay, we will now proceed with the rain branch, and therefore we'll take rain data set. Okay, so we have these records D4, D5, D6, D10 and D14. Okay, now we'll take the first attribute, that is temperature. Okay, before that we'll calculate entropy of rain, which we have earlier calculated 0.971. Now we'll consider the values of temperature. The values are hot, mild and cool. Now hot, there are no instances. So 0 positive, 0 negative. Therefore entropy of S hot is 0 as no hot examples. Then we'll consider mild. We have mild and yes, mild and yes, mild and no. So 2 positive, 1 negative. Therefore entropy of S mild is minus 2 by 3 log of 2 by 3 to the base 2 minus 1 by 3 log of 1 by 3 to the base 2, which comes out to 0.9183. Now cool again, we have 1 positive, 1 negative. Therefore entropy of S cool is 1. Now we'll calculate information gain of S rain with respect to temperature, which is 0.971 minus 0 into 0. Okay, there are no instances of hot, plus 3 by 5 into 0.9183 plus 2 by 5 into 1, which comes out to 0.0192. Now we'll consider the next one, that is humidity. Okay, humidity, let's look at this. We have high and yes, high and no. So one positive, one negative. Therefore, entropy is 1. We'll consider normal. Normal, we have normal and yes, normal and yes, normal and no. So 2 positive, 1 negative. Therefore, entropy of S normal is minus 2 by 3 log of 2 by 3 to the base 2 minus 1 by 3 log of 1 by 3 to the base 2, which comes out to 0.9183. Then we'll calculate information gain of S range with respect to humidity, which is 0.971 minus 2.2 by 5 into 1 minus 3 by 5 into 0.9183. Again, this comes out to 0.0192. Next, we will consider wind. Okay, so the values weak, and there are two yeses, three yeses are there, strong and no's are there, two no's are there. Okay, so S weak, all positive, therefore entropy of S weak is 0, and for strong, all are negative, therefore entropy of S strong is 0. Therefore, information gain of S rain with respect to wind is 0.971 minus 3.3 upon 5 into 0 minus 2 upon 5 into 0, which comes out to 0.971. Once again, we'll write down all the gains. We'll pick up the one with maximum gain, that is 0.971, which is for wind. Therefore, we select wind as the next node for rain. So when we select wind, this is our final tree. Okay, when we select wind, there are its values are its branches. Therefore, strong and weak will be the branches. Now, for strong, all are no's. For strong, all are no's, and for weak, all are yeses. So, we can easily assign labels to it. For strong, it is no. For weak, it is yes. And our tree is completed over here. Okay, this is the tree that we have generated from this particular data set. Okay, if we have some other data set, we might get a different tree. Okay, now whenever we get a tuple to classify, we'll simply follow the tree. For the complete problem, visit my site swativarma.in and decision trees. Thank you.